Yeah, and as Peter said, certainly encourage interaction here.
Oh,
So-
and this one, yeah, just as
Sir.
you're starting, so I am recording it also, so we will be having the slides will be available afterwards in PDF form, and then we will also have the video posted as well.
Okay.
So just
Well, I'm Brian Zonstegger, professional barber. Just kidding. Yeah, so like I said, interactive. You're welcome to interrupt me. But if things start to kind of rat hole, then I'll ask to hold maybe more pressing questions for the end. But certainly encourage interaction, clarification, whatever. And do keep in mind there are two of us, as Peter said tonight. My partner MP here, who also is involved with the IEEE Power Electronics Society with me. You know, the high-level idea here is that we're trying to really raise awareness to make you realize that certainly there's all these amazing projections for IoT wearables, but it's really power electronics that's going to make it happen. And energy harvesting is a big part of that, which is why we really focused on that tonight. And so just keep in mind that a core message you're going to hear tonight is that, you know, this is it's not a lab experiment, it's not nanowatts, it's real usable stuff. But we're going to attack it from a handful of different fronts to realize that, you know, things exist today, it's usable today in these applications, and there's actually an ecosystem already established, and while young, it's growing. So, like I said, I'm Brian Zonstecker. My company is Power Rocks, which is a power electronics consulting firm that give anything and everything in power electronics, but that's not what we're here to talk about, so I'm not going to spend too much time on that. I'm going to cover the first portion of the talk and then turn it over to my partner MP, who's going to close it out. So if you have any tough questions or heckling, I really suggest you save it to the end. And yeah, let's get into it. All right, so obviously, you know, the big question, right? What's going to enable all these huge hockey stick market projections? We'll talk about that a bit. Why power electronics, right? No one cares, it's just a means to an end. Well, I want to make you care. And really, this all comes around one of the main chunk, which is freeing ourselves from wall charging, which is where energy harvesting comes in. And then we see that thermal management is absolutely essential, obviously goes hand in hand with power, and you can't have one without the other, and you can't have electronics without both. Then we'll have some conclusions. In case we haven't completely blown your mind, we'll make sure and do that at the end. So, we've all heard these things in one form or another, right? Okay, tons of devices, huge networks, awesome. All right, and with all these devices, and of course lots of interest and things, exponential growth markets. Now, financially awesome. Okay, but wait a minute, how are we gonna just, you know, it doesn't happen by snapping our fingers, and a lot of these things that have the potential, all these hardware and software hooks are available to potentially make something, but what's gonna really bring it to a reality and enabling is, of course, you guessed it, power electronics and energy harvesting are gonna be a big part of driving this integration. And then I'll also touch on intelligent power management into a kind of a numerator and denominator concept, which I'll show you in a sec here. So, all we really need is just improved battery storage so that we can go, you know, a long time without having to plug anything in, right? I mean, that's the key thing that's going to enable it, right? Well, wrong, right? And that's in my opinion, that's a common misconception that hopefully will get you flipped on tonight. And and just to kind of make the point, as I always like to do is, you know, think about this phone in your pocket, right? Now, the battery in this thing has far more capacity than your cell phone of 10 years ago. Speaking of which, I hope they're all on vibrate too, because I get a nervous tick that goes off when phones go off. But you don't even want to see what happens with this guy. But which one do you charge more often? This one or that simple little low power flip phone with a with a tiny battery from 10 years ago? I think we know the answer. And really it comes down to basic, I consider basic human psychology, which is greed. Right? I come from the server power industry, high power, in the highest end and densest custom power supplies, high efficiency. And you know what? While efficiencies improve and power density improves, the power requirements do not get lower, right? So the overall system requirements for density only increase. And that applies whether it's in a server, a cell phone, or some other tiny device. And why? It's really greed, right? The more power you have, the more crap is going to be architected into that to use up that power. So that's really the main takeaway, one of the really key takeaways I want you to get tonight is a bigger battery is not the answer. As a matter of fact, it has you really focused and going in the wrong direction. So a quote that kind of, I think, exemplifies this is one of my favorites from one of the people I think that's people like to put in quotes of, real visionaries of the industry and, quotes that really stuck through the ages. So we say, yeah, there's no such thing as waste heat, just underutilized energy recycling opportunities. So the point of this here, right, is that, and of course, like I said, notable quote. Okay, it's mine, so maybe not so notable. But the idea here is even just a change your way of thinking, right? Even heat is thought of in most electronics as a waste product that has to be dealt with. And it's not thought of as an energy source to utilize. So keep that in mind. And really now, for all you mathematicians out there, we'll talk a lot about the numerator and the denominator, right? And because when you think about, in a way this is the inverse of power efficiency, right? But it really says, okay, to really optimize your energy utilization, there's two things you can do. You can either reduce how much power is required, right? How much the system requires is taking energy in, or how much storage is available, kind of, and it's referred to as out here. You can argue semantics, but anyways, the point is there's your power requirement, and then there's the power available, the numerator and the denominator, right? If just a bigger battery means we're saying, well, the answer is just to increase this denominator. But we find that exceedingly difficult and impractical for reasons we already discussed and we'll discuss a lot more. So that's one of the reasons I really want to emphasize actually that a bombshell here, the real opportunity for efficient power electronics and utilizing every microwatt, whether it's in an IoT or wearable product, all the way up to the utility scale level and the global power picture, it's really more about reducing that numerator, right? It's reducing the need. That's actually that gets you far more benefit than trying to just create a more efficient power conversion device or have a bigger battery. And so that's achieved through, there's a lot of different terms for it. I call it intelligent power management, right? And there's lots of different ways in the context of tonight's talk that we'll go over this. So different techniques like power management integrated circuit, or PMIC, we'll refer to those. So it's basically a controller that's specialized for power control and management. Maybe includes some kind of conversion, battery charging, and whatnot. Power shedding or dynamic power allocation. So in other words, when you're looking at a system power budget, right, you don't just add up it's not just the sum of maxima, right? It's not just every device in there for its rated max power draw, and you add all those up and that's how much power you need, because again, that would be impractical. It would be, and thanks to entropy, especially with small things like wearables and IoT, it's actually impossible if you do that. So you need to really be smart with the watts you got. So power shedding and dynamic power allocation says, well, if I'm not using this thing as much here, I can turn down the power I've allocated for that, so I have more available over here, right? If I'm processing stuff with a processor, then I'm not necessarily using as much memory. So maybe the memory goes into a lower power state to free up those watts for more processing power. And that way I don't need a power supply that can handle the maximum of both. So, thought-provoking question. right? Does anyone know what the most efficient power conversion device on Earth is? And if you've heard this from me before, then you're just going to have to play along here. But there actually is, you don't have to be a power expert, and you don't have to know a lot of different power conversion devices and everything, but I can tell you there's one very objective answer to this question. Anyone want to take a stab at it? What the absolutely most efficient power conversion device on Earth is? All right, hold on. With everyone screaming at me at once, I can't really hear. So,
Plants.
plants? Yeah, it's an interesting guess. It's true. When I look for the optimum version of anything, usually go into nature. It gives you a pretty good idea. But man-made, all right. But I like your thinking style.
Man-made.
So bicycle, okay. I mean, in terms of actual power electronics conversion, right? When you have to go from one voltage to another, AC to DC. I'll give you a clue. This thing right here, right, as I affectionately refer to as a wall wart, right? Your laptop charger, this huge thing, just for about 65 watts worth of power. This can actually be, and by the way, it's, you plug it in, you look at the data sheet, it'll probably tell you there's a peak efficiency somewhere in the 70–75% range. This can be the most power efficient power conversion device on the planet. Anyone know why? I'll give you another clue. Right now, it is the most efficient power conversion device on the planet. Does anyone know why?
It's like plugged in.
Correct. Right? When this thing's plugged in, you feel it. It's warm, right? Well, heat typically is dissipated power, right, is the inverse of efficiency. It's what's not getting used by the system. Right now, it's cool to the touch. You could argue it's 100% efficient, right? So the point is, how do you make something the most power efficient thing possible? Cut it off, right? And then the next most efficient thing is something that's operating where it's optimized in its load curve to be most efficient. So the next thing is integration, right? If we can shrink it and integrate it, there's a lot of benefit. From a power perspective, going to things like higher frequencies, and we'll dig into this a little more in a minute. Excuse me. Allow you to shrink some of the key components, like some of the magnetics and inductors and transformers, as well as some of the other larger filter components like caps and whatnot that tend to dominate the size and generate loss. But then also, right, the more you can integrate things, you reduce your overhead, so that you have, you can use the benefit of a single upstream power supply and whatnot. And then of course we talked about power converter efficiency. I would hear a lot, especially when I started my career, that in a server board where you have 40, 50 power rails, power conversion. And say, in the next generation, what we need to do, because the customer demands higher efficiency, is we need to push the efficiency of those converters. And all that really does is push a peak point on a curve. But that's not where you're operating all the time. So in my opinion, peak efficiency is a marketing or sales term. It has nothing to do with saving power or actual efficiency, if that's your goal. And because a lot of things, power electronics has come a long way in the last few decades, there isn't a lot of room left, right? When you're over 90% efficient, that means that, in terms of dissipated power, it's 10% loss. Well, it's a huge step to go from 10% to 8% or 5% to 4%. So there isn't a lot of margin left. And just by the way, in my opinion, in case you can't tell, these are kind of in order of priority. So, integration, just to touch on this a sec here. So you might have heard terms, and there's lots of them out there, right? System on chip, in terms of power supply specifically, power supply and chip, power socks, power supply and package, PSIPs, and there's all kinds of creative manufacturing terms for multi-chip modules, 2.5, 3D integration. But the idea basically is that you take the separate chunks and integrate them more and more. Just like it's kind of the same thing we've seen with a Moore's law type of scaling. The more switches you can fit on something, the more you can take off the board for external components. Same idea, concept applies. I'm not saying there's a Moore's law to power supplies, but conceptually, you can understand how we take these parts that were individual blocks and external and integrate more and more. I know this is not a power engineering, power electronics talk, so I won't dig into it too much. But essentially the idea here, and this is even a dated graphic where the future is 2016, but basically it just gives you an idea of scale where, you know, it says, well, where the switching frequency of the converter itself, of the switching power converter, dictates a lot of the overall size and efficiency, density, everything. And so you can see over the progression how pushing the you know, over the timeline here of the year to the switching frequency of it allows you to get, you know, ideally to essentially monolithic integration of the entire power supply, including the magnetics and the larger passives. This was actually done and shipped. I think the largest commercial venture that was out there in production was actually Intel did it, shipped in 2014 with Haswell. That they actually integrated, that it was called FIVR, F-I-V-R, fully integrated voltage regulator, where they actually had hundreds of phases running at hundreds of megahertz switching frequency. Could use air core inductors and all this other stuff we're not going to get into. But the point is, it's already actually been out there. I'm going to see if you just move it along here. Okay. And then in terms of integration, flex circuits, right? We've seen a lot of stuff in flex, but it's been mostly passive stuff. Well, we're getting to the point now where we can start to include some active circuitry in our flex, right? And I'm not talking about kind of what I call the cheating version, which I've seen out there a lot, which is where they take, you know, a rigid or semi-rigid PCB and just kind of slap it on some flex. That's still basically a rigid PCB that's just kind of, you know, co-located with flex. I mean actual flex, right? And here, this is where, so here, and actually I have this for show and tell if anyone wants my backpack afterwards. This is an actual pixel. So there's 3 bare die LEDs. There's an a cap and a driver IC. And these are all direct. This is copper direct on polyimide. So there's no PCB interface or anything here. You can flex this around. This is the relative size of it. What you're looking at is just this guy right here. It's basically like a pixel. So there's 3 of those, and there's a dime. So you get the idea. If you want to learn a lot more about this, actually this gentleman in front here, Shamir, he's putting on an entire full-day workshop in mid-September devoted to 21st, devoted to flex and integration and all that. So talk to him after if you want to learn more about that. I may even be participating in that. And so then there's the other components too, right? Right? Those are actually power supplies, and this is more lab stuff, just recent papers, but just to make the point that, you know, that there's a lot of work in this area here. Now, this is showing that's a paper fuel cell, and you know, it's more than a microwatt. Something usable here. This is something that Samsung put out a couple years ago. These are flexible batteries, so we're seeing more and more stuff in this area from the lab to actual commercialization of products that will enable this. There's a lot more that I simply don't have time to get into. Yeah, that's a flexible battery.
So the thing on the, okay, it's on a finger, wrapped around a finger.
Yeah.
So that's an array of.
So in the paper, it's actually and the whole point is actually for some biometric application, but it's deriving its own power from and I think I'm trying to remember if that one was thermal. Yeah. I believe it's thermal, right? Yeah. Yeah. And we'll talk about that a lot more about just how much power, especially through thermal energy harvesting, is available from the body. We'll cover that in a lot more detail a little later. So, like I said, the real freedom comes from self-reliance, right? Not if I can make my battery, how long I can make my battery last. It's cutting the cord for real. And that's why I say ditch the wall wart, that thing. I don't want to ever have to use that. You know, neither do you. And by the way, you might be thinking about wireless power. There's a lot of wireless power transfer out there. That doesn't really count in my book in the context of today's talk and energy harvesting. because especially whether it's either loosely coupled or tightly coupled. I mean, you're talking extremely short distances, whether it's a millimeter or a few meters. It's still being transmitted by something that's plugged into the wall. So that's not energy harvesting. That's just transferring without wires. And I don't have time to dig into that. And it's also much less efficient. But as we've seen, there's so many sources around us. So that's where energy harvesting comes in. So let's dig into this a little more. So the idea here, right, is we have to build up a case for this. Right? Because anyone who's familiar with anything in energy harvesting tends to think, yeah, it's so small, it's a negligible amount of power, and even then that stuff comes from lab stuff, not real products that are available today and ready to charge. Ooh, you like the pun there? To charge this market, this massive IoT wearable market. But you build the case, right? So if you can have couple of things that generate 100 nanowatts here and a couple of milliwatts there, right? We already have ICs and things today that can actually run on that low a power. And then there are PMICs we'll get into, and they're starting to emerge more of ones that can actually support multiple energy harvesting sources concurrently. So maybe you have a single chip that can take an input from a solar cell and a thermoelectric device to combine that, or something kinetic or whatever. And don't worry, in a second we'll go through a lot of these forms of energy harvesting to kind of help bring up your learning curve. What's out there. And then when you combine that with the intelligent power management I talked about before, right? Remember reducing the numerator. While all this contributes to the denominator, reducing the numerator effectively multiplies the value of each nanowatt or microwatt, right? So we're helping to build our case to kind of go all the way up to even milliwatts, and you're talking milliwatts. Well, now we got something to deal with, right? So, and as I said before, bigger battery is not the answer, right? I'm intentionally and hopefully annoyingly redundant on this concept. Okay, so what are all these? There's lots of flavors of energy harvesting, and of course we don't have time to go into everything. And not only that, but I mean, even just to lay out the many different types, a lot of them are not necessarily self-explanatory. So in the time here, we'll try and kind of give some picture examples and all that. A couple things we will dig deeper into because they're a little more applicable to the really low power IoT wearable application. So dynamo, right? Kinetic energy harvesting or electrodynamic. This is actually the oldest and most prolific form of energy harvesting there is. As a matter of fact, you realize that this is how almost all of the power that we know today on the planet is where it comes from, right? Because whether you're talking, it doesn't even matter if it's fossil fuels or hydroelectric or whatever, all those things almost ultimately do, right, is to spin a turbine, right? And it doesn't matter if it's boiling water or whatever, and it's nuclear or anything. They'll same different means to the same end, which is to spin a turbine. And that's a dynamo. That's harvesting mechanical, kinetic energy and turning into electrical energy. So that's the most prolific one on the planet today. Photovoltaics, right? PV, solar. I think most people are pretty familiar with that in this day and age. I know my father was a solar engineer about 40 years ago. Believe it or not, it was a company called Arco Solar, right? Arco Gas, right? They actually had a solar group down in Southern California. But that's back when the people did that because it was all of it, the only thing you had, something out in the mountains or the desert. And now it's funny. He would have really probably blown his mind to see how ubiquitous it is now. Happy to see that. Piezoelectrics, right? Materials that either, typically ceramics, when you apply a mechanical force, they put power, and vice versa. When you apply a potential to them, they can mechanically flex, so that's a bidirectional property. Fuel cells, right? Something that tip mostly through chemical, biological processes will mimic, as this gentleman pointed out earlier, like plants, right? We take advantage of some of the natural sources around us. Thermoelectric generators, these are materials, again, mostly ceramic, that will convert a temperature differential to usable power. And Seebeck effect, right? You might have heard a lot about Peltier type of things, especially in refrigeration, though that can be reversed and be heating too. And also when MP talks, we'll dig into that particular one a lot more later, so I'm not going to go too much on that. And by the way, just to keep in mind, there's nothing that says these are all, in exclusive buckets. For instance, a thermoelectric material can also be piezoelectric. Anyways, RF, right? There's near field and far field RF harvesting. Again, don't be confused with wireless power transfer, but there's a lot of RF power floating around, right? And well, you guys think of it maybe as usable signal for your cell, but as you know, to have the great quality that you've come to know and love, you have to deliver a lot more. There's essentially a inverse relationship to the cube of the radius, which basically means to get a little bit of power in over here, you have to transmit a whole lot of power, which means there's a lot wasted. So, and everything that's not used in the direct target application means it's available, in my opinion, to harvest from the air. So, and then it's vibration, vibroacoustic stuff, metamaterials, and so then we're getting into the, redundant vibroacoustic. But anyways, and some things that exploit perhaps more than one of these properties, like the example of the thermoelectric and piezoelectric generator I was referring to before. Okay, so cool, right? But it's just a lab experiment and all this stuff, right? Okay, well, you probably figured this out my little game by now. Wrong, right? That's not the case, and I'm going to make you a believer of that tonight. Even with just a short list of things that exist today. Believe me, this is a short list. You're not going to believe it when you see how busy this slide is. And probably a lot of these are just bullets and a lot of words that make your eyes roll back in your head, but I'll also have a little picture show and tell to go along with this. But essentially, these are all, so on the transducer side, right, the sensors is something that's going to actually convert. There's many companies that are shipping devices today or selling IP or licensing IP in this area. But there's tons of this stuff. This is just a brief list that and there's stuff that covers all those things I talked about, all those different forms in the last slide. So again, these are all commercial products, not lab experiments. And for the ICs and the management and power conversion in this, right, the PMICs, you see all the top players in the industry. I'm sure you recognize these names and even some smaller ones that you may not traditionally think of as being involved in power conversion or energy harvesting, either directly or indirectly, actually are. And not only that, it's, and some of them, like Linear Tech, actually have 25 products. And that's not just like, I'm not talking about 10 part numbers because of different packages and stuff. I'm talking about actual different products with a lot more to come. All these guys have, I said, this is just the beginning of this stuff. And there's kits, eval boards, things where that kind of marry the controller stuff and the transducer, the sensor, the harvesting elements to make something useful for you today. So you don't have to, figure out how to capture it and do battery charging or some kind of energy storage and convert that to power and all that. These things all do it for you. And just to give an example, right, because they know that the market that we're all mostly focused on for this, they have to be extremely low power, right? They have to, while they're helping to provide the numerator, the denominator, they also need to make sure that they're not consuming much of that numerator. So just as an example, and this isn't the lowest one I could find or anything. Actually, this is just, many part numbers, I just picked one out of the hat, looked at the spec sheet, and so the quiescent current for this TI controller is 325 nanoamps. That's not in a sleep mode. Okay, and a lot of these things, I mean, actually integrate, you know, processing cores, memory, all the fun things we've come to know and love in SoC type of things, and require so little. So you can use that today. And they're set up to accept multiple sources and storage elements. So whether it's storing, you know, some energy in a supercapacitor or rechargeable battery from your energy harvesting source, and then as a backup you have a coin cell or alkaline or whatever, they're set up to do that type of stuff. And they'll actually convert it to a usable power rail for whatever your end, you know, your 3 or 5 volts for your end target device or application or whatever. So, all right, but what about the ecosystem? Well, as we're talking about, there's many, so you've seen there's many products by, you know, players in the industry. And by the way, just to preface this, I don't represent any of them. I'm not trying to sell or push anyone's particular stuff. Really, the whole point here is awareness, right? Just making you aware of it. I don't care whose stuff you get, as long as you look into it and get something and make it realize it's the reality now. So there's lots of events, initiatives, groups, and everything that are devoted to this. And I selfishly happen to, there's far too many to list here. I could easily, between that and events, I could easily list 20 things. But instead, I picked the top, whatever, 3 or 4 that I tend to be involved with. So that's why I selfishly picked. So one of them, the Power Source Manufacturers Association, they have an energy harvesting committee, which I sit on. That's actually, if you saw, that's what this is kind of the synopsis in a picture. That's what that poster is. And if you really liked it, come talk to me afterwards. I can give you, I got some flyer versions. The IEEE Power Electronics Society. Well, okay, I chair that, and he's the vice chair. But we do have we cover the full spectrum. But we're actually targeting putting on a full day energy harvesting workshop towards the end of the year. More to come on that. APEC is kind of the premier power electronics conference for the industry. Annually, there's a whole session, industry session they call it, devoted to energy harvesting. A lot of the folks involved in these things will be presenting there. But the point is it's, and like I said, this is the premier event for the industry, and it's an IEEE event, so it's not, this isn't a commercial thing. Like the next thing, for instance, there's some coming up here in the fall, right, ID Tech X, which has a lot of things, but just making the point, right, they have a whole energy harvesting event devoted to this too. But this is reaching the mainstream. The ecosystem is here. It's young, it's nascent, but it's here, and there's a lot of room for growth. So I'm going to quickly fly through just a couple of examples, just to show you that this isn't just a bunch of stuff that I'm pulling out of my ass and making up stuff and putting a bunch of words and bullets, right? There's some real tangible stuff here. So here's an example for photovoltaics, right? This is a commercial product. I just saw this at, I think it's CES, I don't know, last year, this year, right? That's a phone charging case, and you know, it's not, of course, it's not going to be the equivalent of plugging the wall. But if you're outside in full sun, you know, you probably get, you know, if you have 15 minutes, you probably get enough for a phone call. And if you're trapped somewhere where you really don't have a source, though you probably don't have a signal either, you'll really appreciate that. And you'll probably have some time to kill. This is an example of the Alta devices. They make gallium arsenide flexible solar cells. So these are, you know, these little tiny ones. So maybe you've seen a lot of things like BLE sensor type of things that are run off of, that can actually take advantage of indoor light, indoor ambient lighting, as well as outdoors. This is just an example of that. And they're little tiny cells, as you can see, but you can put them together and make something as big as you want. RF, as I talked about. Now we talked about wireless power transfer, which the concept is there. And you know, the physics and everything are the same of taking your power and boosting it up to a the frequency and up to the point of resonance between a transmit and receive coil. Won't get into that, but the point is you can do it. These guys can do it with, you know, near field wireless power transfer. Then you can steal it from the air too. These guys, we're going to something like that. And a concept that's really used a lot today is RFID stuff. right? You know, those little RFID tags, that maybe you have them as asset tags in your company. Maybe when you go through the toll, you know, the fast track tag, and you go through it, it beeps when you go through. You know why? There isn't a battery in there, right? That's actually, the thing that's reading it is also actually transmitting enough power, just enough for it to run and send a signal back. That's energy harvesting. I always thought this was neat. This isn't the video here, but you can actually see the video. This was just a IEEE Spectrum thing, but they used, I think it was mercury or something similar to it, right? Where applying potential, they could actually change the amount of this liquefied metal in here at room temperature, which essentially means it's a antenna that changes on the fly, right? And what that means is if you can adjust the antenna length on the fly, you can adjust to different transmit and receive different frequencies. It's a negative impact because, you know, you can also think about things like 5G coming, where if you think there's a lot of RF power bombarding us now, it's nothing compared to what it's going to be like when 5G hits the mainstream. And so, yeah, maybe we could steal some of that. Maybe the guy next to us doesn't get as much a great of a signal, or someone in the neighborhood, but you're using more of that power. Thermoelectric generators, just to give you a taste, and again, MP, when I turn it over to him here, he's going to really dig into this. But, you know, this concept from the Matrix, right, you remember that? That makes a good point, right? We actually are batteries, right? And depending on what data you look at, it's really on the order of, you know, even when you're just, you guys sitting here right now, you are 100 watt-hour generators. That's a lot. That means that if you harvested just the thermal energy you are putting out, right? You could power a light bulb. Probably not the one that's in there, but maybe one of the ones you used to have in your home before you replaced them with LEDs and whatnot. And when you're really working, when you're running down the street or whatnot at the gym, right? Over 500 watt hours. It actually should be watt hours, not watts per hour, but oversimplification. But anyways, the point is, you got to pull your phone out of your pocket, right? It feels warm, right? And hopefully it's not because the ESR and your battery's discharged and it's actually coming from the battery generating it. It's because it's been sitting right on you and you're warm, right? You're 100 degrees, right? 98 Fahrenheit, 40 C, 38 C. And so, and this was just some paper. Really the takeaway here, and by the way, this is 2008, this is old stuff. Just showing that if you just put a little thermoelectric generator between the CPU and a heat sink, you know, you can get milliwatts of power, and these materials have come a long way since then. And so if you feed that back into the system, you know, you say, well, that's maybe pretty negligible. Let's say it was 0.1% or 0.01%. Of all the power consumed by that computer or that server. Well, when you scale that, that's pretty freaking significant, right? To put a little device in there that you would have considered waste, and you would have actually spent more power just to remove, and now you're utilizing it. So you're really getting huge benefit across the board. You know, if you reduce the global footprint, the data draw of all the data centers in the world and reduce it by 0.01%, I can tell you the number off the top of my head, but believe me, it's a big friggin' number, okay? That represents about, on the order of 10–12% of the total world's power consumption. So even 0.01% of that is nothing to sneeze at. So with that, I'm gonna turn it over to my partner MP and quit yakking. And then we'll both at the end here, we'll come back up for the conclusion part, and then we'll field questions together. MP.
Thank you. Okay, so I guess there was a lot said about various ways of extracting energy or waste heat or whatever. TEGs, or thermoelectric generators, are one of the major ones that we are focusing today in this presentation. So common among them are by the way, the idea is very simple. It's reverse of a thermocouple. So you have two dissimilar materials. So basically, there's a thermal EMF generated because of heat delta, or the heat differential. So I'll come to that. Delta T is a major number in TEG, the thermoelectric generators. So among them, the telluride semiconductors are the most promising. So in that, there is this number called the figure of merit, or ZT. So that is the highest, for telluride. But unfortunately, they are limited to lower temperature applications. So if you have an industrial scenario, you're better off with the lead, the lead telluride, the PBT or whatever that compound is. They are ideally suited if you're, let's say, you're trying to extract energy, waste heat energy from an engine, which is much higher than the human body temperature. Maybe runs into hundreds of degrees of Celsius. Jet engine, for example, those are most ideal for those. So majority of the discussion that we're going to focus today will be for the consumer applications, like body wearables, things like that. So we'll focus the attention mainly on those. So earlier, I guess we mentioned about thermocouple, that's a LTA effect. The reverse of it is CVAT, which already has been discussed many times. And sometimes I use the word CVAC generator, that just means a TEG, basically. So they're already here. They're used in power plants. Automobiles actually is one of the most common application. With respect to human body, it is very intricate. It's not as clear-cut as it is for industrial applications. And the trick here is we need to maximize the delta T. So the human body temperature is about 98.6 degrees Fahrenheit, which is about 37, 38 degrees Celsius, right? So that's really at the hot end of the scale. So let's say you're going for a hike in Nevada, and the temperature is about 42 or 44. Intuitively we think, oh, there is a lot of heat available to harvest, but from a delta T point of view, it's not as great because you're only getting like 4 degrees delta. On the other hand, if you're hiking in a cooler weather, like 20 degrees Celsius, you have the maximum delta T. So that works to your advantage whenever you work with the TEG CVAC generator. So we said a lot about Internet of Things and the sheer volume. Years ago, when all this, the initial stages of the hype cycle, whatever you want to call it, began, I was trying to do some common sense calculations. And one of them was, there still is a prediction of trillions of devices, right? There is this trillion sensor MEMS conference too. So I was on the back of the envelope making some simple calculation. If there are a trillion devices and each one of them has, let's say, maybe 10 square millimeters of area that needs to be plated with gold or silver, 6 microinches, that's not a lot. So if you do the numbers, then you come to a realization that, oh, sure, we cannot use precious metals to do this kind of things because we'll run out. So there is really a materials issue when we talk about sheer number. And the same thing applies for energy. If all of these have to be powered with lithium batteries, I don't think we have enough lithium in the world, to power all of these, gadgets and devices. And also, we have not gotten that good in recycling and reclaiming, wasted materials from these batteries. So the alternate is we have to do this energy harvesting. So it's not just a theoretical idea, a wish list. It is a must. Otherwise, we don't realize, what we are forecasting. So for IoT, it is when Brian approached me, I was taking this in a much more general sense. And the reason I'm saying this is I had to balance, energy harvesting as it applies to industrial, including data centers, as well as personal applications. And it has a lot to do with what we call as the touch temperature. So as we were saying a minute ago, human bodies, our temperature itself is already 37, 38 degrees. And if you have a wearable on your arm and it is running at 50 degrees C, you're already burning your skin. And it may be, almost like a permanent damage, a third-degree burn that you cannot, recover. So we are limited to the operating temperature that's much lower, about 45 degrees tops. So what this does is it compromises the performance of the SoC. So in other words, you need to clock down your processor, to make sure that you stay well within the limits of human body's tolerance. On the other hand, if you're dealing with let's say a gateway, an outdoor gateway that has all the radios, Bluetooth, Wi-Fi, Zigbee, and also has compute node. And even if it is a 45-degree or 50-degree Nevada weather, we have enough margin because there is some air. Even in still air, you get some convection. And as long as the junction temperature of the CPU stays well within, for silicon, it's about 125 degrees Celsius, you're okay. So the point is, these case temperatures or the body the touch temperatures have different meanings in different applications. So today we'll focus mostly on wearables, body wearables. And by the way, one more comment. These are external wearables. I'm not sure how many of you know the embedded ones. Have you heard of those? There are embedded wearables starting to come into the market. So there is this company I wonder how they do energy harvesting because it's embedded in a palm. So talk about finding your true north. What this chip really does is it has a magnetic chip and a very tiny piece of substrate, and it's embedded into a palm. So if you're lost somewhere and you don't have any power, you hold your hand in some direction. Finally, it glows when you're pointing up because it's got a magnetic chip. So there are a lot of people. This is what is Generation X or Y or Z, right? So they're not like what we were used to or what I was used to when I grew up. I didn't have any wearable, but wearables has gone to the next stage where they're becoming embedded within the body. So the only embedded one I knew was the pacemaker from my days, but that's a different one. So so with this, the way to approach thermal management would be find out where the application is, and then and by the way, this is some of the material that we have already discussed. So in some of this I already alluded to, like the edge compute ones. We have typically the case temperature 55 to 75, and there is usually about a buildup of about 25 to 30 degrees, sometimes 45 degrees of temperature buildup going to the CPU's junction, the processor's junction. On the other hand, wearables, human wearables, we are forced to operate in the 40 to 45. So what we have to do right now is, if you're working in a wearable and you're designing a brand new product, so it's all about how you want to partition your design. In other words, there is a typical Fitbit or maybe even an iWatch. You have a big dial and then there is a strap. So now you need to think about partitioning the design that you're taking best use of every available square millimeter. So in other words, just like Brian was alluding to earlier about the flexible electronics. So if you have an embedded battery technology, a thin film battery technology, you would rather place them in the strap. Or antennas, for example, they go in the battery and not necessarily in the main dial. So this way you're taking, making best advantage of every available space. At the same token, you are actually spreading the heat much more uniformly throughout the body. So now it can work both ways, and this is where the trick lies. Let me stay on that one before I come to the next. The trick is, on one hand, you want to optimize, the CPU, get the max performance. At the, when the max performance happens, you also have the max waste heat, so that the temperature goes max. At the other end, you need to make sure that you're getting the body temperature to the ambient temperature delta to the max. So you're designing a system that balances harvesting versus thermal dissipation. So it's very tricky system level type simulation that you need to do. When you start partitioning your design and you run some simulation, you figure out where the temperatures are. And of course, this would be more of a very complicated system simulation, where you're not just simulating, the thermal dissipation using finite elements like ANSYS or whatever, but you're also looking at the energy harvesting simulation at the same time, and then you're doing the entire system simulation. Some of this data, by the way, this is I think from ASTM. This tells you, what the gain limits are. Most of them, for example, I think once you cross from 40 to 50 degree, you have severe. Some of them are first degree, but the third degree burns happen at much higher. There is much more on this. Incidentally, there is this one case that if you guys look up this particular spec, ASTM 1055, there is one case where Someone used that, this was a lawsuit that was brought up by a lawyer. They used that for the situation where, you have a glass door in front of the fireplace. So most people, sometimes kids go and touch that and the fireplace has some wood burning. That glass does get very hot, and we usually teach kids not to go there, but sometimes accidents do happen. And so that person actually used that spec successfully, to sue the vendor who was making the glass door. And it turns out that it goes way beyond 50 degrees. So even 3 seconds of contact can burn the flesh for 30-degree third-degree burns. Some of the examples, and by the way, Brian mentioned a good number. I think most of us sitting here are 100-watt bulbs basically. But unfortunately, as he was alluding to, look at the tiny area. So in that area, the most you can get is few tens of milliwatts. Now that may be enough, to keep the battery alive, throughout the day, as long as you have the battery charged and it's on a quiescent mode. You're not querying it maybe every few minutes. You have a poll data that sends it up to your mobile, so it tells you a heartbeat or pulse oximetry or whatever. So that operation may be enough by the harvested power, and it may very well be that you can wear the wearable for like days on end and not have to charge it. And those days are here, but the challenge is, again, compromising the max operation, the clocking of the performance of the processor versus the temperature that you need to maintain versus the power you can get. So it's a more of a system level optimization challenge. Most times, we get between 10 to 20 milliwatts, per square centimeter. That's the most power you can expect to get. And this is, by the way, it's an excellent source if you guys want to look up energy harvesting for wearables. Wearable monitoring systems by Bonfiglio or Girassi. It's an older book, but I think there is an update on this. That's actually a test vehicle that they used. And by the way, another thing that I forgot to mention, most of the wearables have almost like a 2D geometry. The thickness is very minimal compared to the XY. Right? Now, in terms of energy harvesting, that's not the best geometry. You need something in the third direction so you can get the maximum delta. And that's the reason why you're seeing a heat sink here, because they're trying to capture the max delta. There are already many vehicles, many examples that you can actually, I think some of them do sell the eval kits. They do use, I think you were mentioning TI and then N-Ocean. So there is this company that licenses their material, energy harvesting material called Cymbet, CYMBET. That's another very popular material supply.
Battery in a chip.
Correct, but they do battery in a chip, and that is becoming very popular. So now, and by the way, I didn't post too much about my startup, and one of the big motivations was really, I started that effort, thinking that I still believe in it, of course, that the whole design process has changed. It used to be that you build a system, you build a board, and you build a box around it, and that's how this projector was made. But you do a wearable, it's completely different. You go to an industrial design house, and then they design this cool-looking shape, and the strap, and the features it should have. And now you go backwards. You start from that topology, then you design your product around it. So that was the whole idea about stack design. So anyway, this there are a whole bunch of examples of wearables that are already there in the market that do use energy harvesting, body waste heat, or radiated heat. But here is something that I was describing earlier, and this is, as you see here, towards the cold end of the air temperature, you get the max, because the delta T is the max. And as it gets warmer, you see a very gradual decline, in energy that you can harvest. And this, as the previous slide was showing, varies from people to people. I mean, we all have different body chemistry, and the thermodynamic rate is different for people. So some people may have a lower end of the scale versus some higher end. But overall, there is enough power, to keep a charged wearable continuously charged for almost indefinite period of time. So that's where we are at the current state of products that are available in the real world. Now, earlier there was a mention made about metamaterials. Now, these are materials that perform at higher, material characteristics. Typically, these are engineered materials where you tweak the properties by making the material at a much smaller scale than the wavelength. So let me qualify that. For example, for thermal, we are really dealing with IR, infrared radiation. So in IR, you have the short, the mid, and the long. And depending on which market you're addressing, you can make the arrangement of the crystals in such a way that the spacing is much shorter than the wavelength of the IR. Let's say, for example, for argument's sake, let's take 850 nanometer, which is the short IR. So if you come up with a material, let's say aluminum, particle, powder aluminum, and then you make a different formulation of it such that the particle-to-particle, the particle matrix is much smaller than the 850 nanometer. Now we have a meta material in aluminum that has maybe 3x or 5x the conductivity. So those things are coming, and with materials like those, I think we should be able to see more. But as of now, by the way, there are many factors to this, and one of them is the thermal conductivity of the skin is pretty lousy. It's barely about 0.5 watts per Kelvin. To give you a comparison, gold is upwards of 400, so it's almost like many orders of magnitude better. And the other thing is we also have skin oils, and there is sweat. So as your wearable contacts them, there is this thermal resistance that builds up. So in reality, we may be putting out more power than what you're seeing here, but because of this thermal impedances of the so-called biothermal impedance, we end up harvesting much less. Okay, so this is, Brian, you want to run through the conclusions?
Sure. So just to sum up, thank you, MP. Essentially, obviously, power electronics and energy harvesting, hopefully if you weren't a believer before, you are now, are absolutely essential to trying to make all those market projections correct. If it's going to be useful, it's essentially have to operate basically forever without a charge from the wall. And that's really the goal and really the key to the billions or trillions of devices, as MP pointed out. And a lot of that is enabled with, and it's a good point, I actually wasn't aware about the need to also produce precious metals and limited materials too. It may not be mathematically possible even, which is another great motivation. I'm stealing that. So as the real takeaway is reducing the power demand. So reducing that numerator, big focus on that is really far more important than increasing the denominator. And energy harvesting, it's not a lab experiment. Ecosystem, well, nascent, exists now, and there's a lot more to come. But it's already in the mainstream, and there's more. And then, as MP detailed, right, being efficient with power also means being more efficient with your thermals. So, with that, we thank you very much for your time and attention. Welcome questions. And just so you know, it sounds like we're throwing up a bunch of pretty pictures and maybe just making all this stuff up to sound cool. There is copious references for all of this at the end of this. So like Peter said, the PDF will be available for you to download, so you can look at all this to yourself and tell me I'm full of crap, or hopefully, more importantly, become an evangelist yourself. So thank you very much. Questions? Concerns?
So the thermal energy harvesting, I appreciate the overview and the details, but for wearable devices on humans, it doesn't look like it's practical.
It is practical, yes. But it's not a replacement, it's an augmentation for the batteries. A complete replacement, well, let me take that back. You can make wearables without any battery, but you do not have the same function, like let's say Fitbit or an iWatch or any other one. You like to trim down, what you can do with the energy that you harvest. But as a backup for charging battery, it is really great.
And so, and to tag on to that, I mean, really what you're talking about is even get away from this concept of battery. Well, you really need some kind of energy storage, right? It doesn't necessarily need to be a battery. And it also doesn't necessarily need to be long-term energy storage. In other words, really dense energy storage, if you can replenish it more frequently with the free energy that's around you, which is where energy harvesting comes in. And specific to your question about thermoelectrics, right? Like MP said, it's all about the delta T,
Yeah.
right? And so if things are close to each other, there isn't a lot of power to grab from that. But what's actually more common, he's showing is that typically even the ambient environment is going to be much different from your body, right? Typical room temperature, 25 C. Right, which we'll assume it is now. Maybe it's a little warmer in here because you're so excited on the materials we just discussed. But which is good because then it means your body temperature, which is around 37, 38, right? The bigger that differential is, the more there is to harvest. And even more, means in the upwards of tens of milliwatts. Well, we've also shown if you look at spec sheets for any of these things, or small ARM processors, mobile things, that's actually enough to do something pretty significant.
I guess, yeah, so thanks for the explanation, but I guess my reaction was that when you looked at those example wristbands from one of your later slides, they're very big, they're very bulky, they don't look like they're practical.
Right, and that's a major drawback. But ideally, for example, if you want to build a energy harvesting, watch, you want the TEG to be on the top surface, because that's where it needs to be. Because it needs to, to be in touch with the ambient temperature, right? Ambient air. If you put it underneath the watch, it's not going to work. So, and at the same token, you need to not block the, the main dial of the wearable where the display is, and so in that scenario, so you're really restricted by how much you can harvest. So now push that to the side on the strap. There is a completely different use case, and you can do much more. So, but it increases the cost, increases packaging methods and manufacturing. So these are cost adders, and as of now, they're still not very standard.
But I'm sorry.
So there has to be, there is really good room for growth in this area, where you come up with this. Package used to be just a dumb box. Till wearables and consumer devices came on board. Now they're becoming more functional, smart boxes, so to speak.
Do you guys know that this thing around your phone, these are your antennas?
Yeah.
Yeah.
So now it's a question of engineering them to make the best utilization from them, and energy harvesting is the most perfect way to do that.
And keep in mind, one of the things we talked about here too is don't be thinking that any one of these is the answer, right? It's utilizing all your available resources, which may include multiple sources of even energy harvesting. So like in the wearable device, the example that you were referring to, while we say that they're the kind of the front runners as they exist today, like thermoelectrics and solar, right? That the devices, the PMICs that are around supporting these are being designed to support more than one concurrently. And that's the reason, so that everything contributes to the pool to make sure the pool is still usable. That's just a key takeaway.
Right. One other point I want to make with respect to PMICs, and by the way, I don't work for Qualcomm. I don't get paid for saying this. Werable was here somewhere.
He does, so he'll keep you honest.
So he works for it. He didn't pay me, honestly. But one thing they did, was they have this new SoC, Snapdragon Wear 2100. It's specifically made for wearables, and it is almost like 30% less power hungry than the predecessor. And the other thing they did is they moved some of the modem codecs and into the PMIC because they wanted to save space on the SoC, so they pushed that to the PMIC. So it's a question of doing an intelligent engineering or efficient engineering and partitioning it, which is what I was alluding to.
In the context of the language we used tonight, right? What they, in that example, like with the Qualcomm Snapdragon, right? They made a big point to reduce the numerator, and also with integration, they were able to take advantage of the overhead that had to be accounted for individually before. Anyways, some other questions, sir?
I had a question, just to give us some relative idea of where these technologies are, right? So if I'm doing a wearable and I think about, okay, what kind of harvesters could I use? I mean, the thermoelectric is one, vibroacoustic with, something that's piezoelectric or vibroacoustic from movement. Maybe you have something, I don't know, RF harvesting, energy harvesting. So, I mean, you get the message I'm kind of getting is thermoelectric seems to be the furthest along in terms of its ability to generate power. But in relative terms, where if you were to do an RF device or a vibroacoustic device, is it going to be half as good as a thermoelectric? Is it an order of magnitude lower?
Well, so
where's the state of the industry?
You're asking a very application-specific question, and like anything else, right? I mean, you want to kind of say, well, what's the takeaway kind of rule of thumb, easy answer to help get me going? And of course, maybe it's just because I'm a jerk. I like to answer loaded questions with loaded answers. And so what I'll say is it's application-specific, right? It depends. So what I'd recommend in terms of your flow of this is, first think about what your specific application is, right? And then think of the operating environment of that specific application. And then use that to think, well, what are the, typical or most, let's say, abundant types of energy sources available? And that can help you converge on the actual type of transducer that or energy harvesting technology that you may want to focus in, right? Because even, for instance, let's say you realize, okay, it's a thermal differential, like you're talking about, so I'm a thermoelectric generator. Well, is that just the answer? Well, you can go into that, and you can see there are, very commercially easily available things. If it's lower cost for a consumer thing, the quantum efficiency, it doesn't convert as much power. In the same volume, you can get a thermoelectric material that will provide much more power, but it's a much more expensive material. So like anything else in product development or anything, right, it's a question of application and all those other fun business things like cost and assurance of supply and manufacturability and all those things. There simply is no easy answer that says if you're doing this type of thing, use this, and then,
I think your question was more on an apples-to-apples comparison, right?
Yeah, I was just, like I said, the application would be, if I'm thinking, take the use case we're talking about here tonight, a wearable device, right? A PV cell probably, unless you're outside, it's not going to make much sense. But if you're in an office environment, you have movement, you have RF around you, you have the thermal differential of your body.
Right.
In relative terms, just, where are these things
So the TEG,
in terms of maturity?
right, in thermal, in terms of thermal harvesting, it's a more than an order of magnitude higher than ambient RF energy.
Okay.
But outdoor, definitely PV beats it.
Sure.
Actually, sure, I remember you had your hand up a long time ago.
Yeah.
Sir?
Allegedly, Nikola Tesla did wireless power. More recently, P-Cell Wireless, Steve Perlman, Artemis Networks is a new cell phone technology. It's supposed to be location, super fast internet, and possibly wireless power. There's also been, a few years ago, some people powering some kind of IoT device with Wi-Fi, just the energy from Wi-Fi.
Yep, that's far field RF harvesting. So to answer your first question, it's not alleged, it's well documented that Tesla definitely was I believe the first known to demonstrate wireless power transfer. But what was maybe more alleged from what I've learned about it is he actually intentionally buried that work initially because of its potential as a weapon, and he didn't want the government getting a hold of it. So it didn't actually come out until after he died and they raided his lab, I believe is what I recall learning about it. But yeah, there's tons of that stuff out there. And it's, like I said, it's not a new concept. It's really, it's not a matter of being able to generate power or enough power. The real question is usable power, right? And if something like you said, if it's coming from Wi-Fi, right? Everything that's a signal that's electrical, even digital, ones and zeros, right? At the end of the day, those are actual analog signals. That is all power.
Right.
It's just a matter of if it's usable power to you or not in your application. And if your application requires so little power, then it becomes usable to you. Was it related to that? Because there was another one that had a question too.
So, I mean, you said earlier on in the beginning that wireless power transfer is not very efficient, which is true, right? In order to generate 10 milliwatts and you need 1,000 watts coming out of the wall or something like that. I made up the numbers.
Yes.
But if you don't care about that, right, you're just looking for something that's portable, that's self-powered,
Right.
based on an ambient, or power that you pump into the room. Yeah, is it viable? Is that a viable approach?
Well, sure, today, but again, it's how much do you need? I'll give you a really, this kind of, I like to get to more fundamental concepts on this, but so I'm a power guy, right? And I travel a lot. I sit next to people on planes. They hear I'm a power electronics person. The first thing they always ask me is, oh, what are you going to, make it so it charge less longer, or a bigger battery? And I say, well, tell you what, I'm a magician. I don't even need to re-engineer a new device or make you buy anything. I said, I will increase your battery life by 20% right now. And I show them a little feature called auto brightness. You know what? Or I do another one where their phone's sitting on the tray and it's open like this. Say, I'll do it right now. I said, simple. I just hit the button and turn their screen off. Because the screen is one of the biggest consumers of power. Right? That's intelligent power management. So, that's really that's why we've been able to come as far as we have and squeeze in as much junk, even today, by today's standards, because we do it more intelligently. On processing, right, we actually turn off processors, in on and off in the millisecond time resolution, right? Because saving 1 millisecond, in the grand scheme of many milliseconds, saves a lot of power. So again, numerator, denominator. Sir, you had a question?
I just want to know, other techniques like harvesting, what's the efficiency compared with each other? Which one has a...
In terms of wireless power transfer?
You
mean compared to a wired device?
Compared to all the list.
So,
The harvesters.
well, so again, there's no one answer. In terms of quantum efficiency and all that, right? There's theoretical limits. There's, take solar, for instance, right? I think the theoretical limit is something like 34% quantum efficiency. But you can go and
you can get 46.
But there are techniques that go beyond that will look at multiple wavelengths concurrently. We'll take solar. Actually converting solar electricity, and you take advantage of solar thermal at the same time. So that there are other things techniques you can take advantage of. There's many different materials that are optimized for different things. And there's actually the government, where's the page that publishes data? Like I said, I just use just one of these alone. You could look at all the different, there's organic, there's silicon-based, there's many different types of solar where they're hitting new efficiency records, but that's why there isn't one efficiency, right? It's very dependent on the type, the application, how much money you're willing to spend. Where did I have this thing, right? These are gallium arsenide based stuff, and that's because that helps with the flexibility, and also they've made it where it can be optimized for different wavelengths, so you can actually capture power outside or inside. But you have other devices that are maybe only outside or only inside or only infrared. So hopefully you get the idea that it's really hard to just simplify and quantify it to a number. Any one of these things, I'm sure you can see something that operates on the end of the spectrum. Now, they're not going to be, most of them are going to be in the ones of percent of actual quantum efficiency, which would probably be regarded as pretty damn good for most of these things. But again, it's in the context of how you need it, use it, what you need, and 1% of free energy is a lot better than 80% of something you pay for, one might argue. Yeah.
If more specifically for the RF transmitting, what do you think, in which areas RF transmitting can be improved?
Well, that's a whole other, that's a multi-hour discussion in and of itself. But even some of the things the standard that exists today. You're talking about this stuff. You can even theoretically get in the 70-80%, and they'll show you that, especially in tightly coupled harvesting where you're talking millimeters of distance.
That's near field, right?
But that's also dependent on, a perfect coupling between the transmitter and receiver coil, and it has to do with, the complex impedance, Smith chart type of stuff,
That's right.
where, not only is it perfect alignment of coil to coil, but the angle and all that. So even in a lab, if I can show you that I can achieve, let's say 80% efficiency in that transfer, which is roughly equivalent to the wall adapter that I was using, that's in a perfect ideal situation, and I guarantee you, your average consumer, the way it's used, will not be anything close to that. And so if the average people, if it's all out there, millions of people are using it, and the way they use it in general, say they're closer to 40 or 50%, then globally, we're really losing. It's a big step backwards in my opinion, but you know what I mean? And what it really is we're trading convenience and cool factor
That's right.
for efficiency and carbon footprint and all those other things. But your average consumer is not aware of that. They just think, it's cool and maybe it charges a little slower, but they may not realize how much they're actually giving up for that.
Shomuri had a question, right?
Well, I said, you mentioned that there is RF power sources. There's this company that's actually come up with a transmitter receiver set where the transmitter is wall mounted, and you could be as much as 15 feet away.
Yeah, you're talking
And
about
can get up to
these guys.
a total of 10 watts
Yeah,
on
Yeah.
multiple devices.
yeah. They're just, well,
Was it way
see how well it works, one.
Right.
And two, that the real question is, well, how much power do I have to transmit to get that? And that's where the efficiency number comes in and really makes a difference. And I'll tell you, I guarantee you it's a hell of a lot more than if you plugged in all those devices.
And there are SAR limits, right, specific.
And then there's the actual safety stuff and all, and I don't have time to get into. I mean, even there's limits on individual device, right? Even the jury's out on even on these things where, well, if you hold it next to your head for decades and it's all around us, in my opinion, the jury's still out on that, even if there's established limits on a single device.
Yeah.
Same thing with when we bombard ourselves with even more RF energy. But if we harvest it, then that also means that it's being used for something instead of ending up in our tissue and other undesirable places as another added bonus.
Question here.
Sure.
Two questions. Vibration